In this lecture, we're going to take a look at Mendel's second law, the law of independent assortment, and we will also take a look at the use of statistical analyses like the chi-square to evaluate patterns that we observe from genetic transmissions and whether or not those are statistically significant or influenced by random forces. So we will review a little bit of the history of Mendel's dihybrid cross experiments, and we will look at chi-square, goodness of fit testing, as well as some basic principles related to hypothesis testing in science. So when we think about the dihybrid cross, the purpose of the dihybrid cross is to examine multiple traits at a time, and Mendel used these experiments to unravel the principle or the law of independent assortment. To set up the dihybrid cross experiment, Mendel performed a similar series of experiments that he did with his monohybrid cross. He created true breeding populations of plants, but in this scenario, he created true breeding parents that differed in two characters, and then crossed them to create dihybrids in the F1 generation. And dihybrid just means that they were heterozygous for both of those particular traits. And then he crossed those dihybrids together in order to understand whether or not the characters were transmitted as a package or independently from one another. So if we think about how this could potentially work, here we have a pure breeding population of pea plants that always produce seeds that are yellow and smooth, and we have another population of pure breeding peas that always produce seeds that are green and wrinkly. Now, if we think about this, there are a couple of different possibilities. If the Y and R genes, the ones that control color, so let's say that this is our setup here, okay? And then R is round, which is dominant to wrinkly. If the Y and R genes must be inherited as a package, if, for example, in this scenario, being yellow means you must be round, and being green means you must be wrinkly, then when we look at the dihybrid, there are two possibilities. If they are linked, then the dominant Y and the dominant R must move together in the same egg or sperm, and the recessive Y and the recessive R must move together in the same sperm. But if the decision for color in no way influences the decision for shape, then there are four possible gametes that this individual can produce. So if they're linked, if color and shape are linked, if they're inherited as a package, then the first parent will produce a sperm that has two dominant copies and two recessive copies, and then the other plant will produce eggs that are of the same pattern. And if that was the case, what Mendel should have observed is a phenotypic ratio of 3 to 1, which is the same that he observed in the monohybrid cross. So if the two genetic decisions are linked, the one for color and the one for shape, then the dihybrid cross experiment should come out the exact same way as the monohybrid cross. If, however, there is no connection, no linkage between the yellow or green and round or wrinkly decision, then you can have each parent producing 4 possible gametes, which doesn't give you a Punnett square of 4 squares, but gives you one of 16. And of course, what Mendel observed was, in fact, this scenario. where 9 of the offspring were dominant for both color and shape, 3 were dominant for shape and recessive for color, 3 were dominant for color but recessive for shape, and 1 that was recessive for both. This 9:3 to 3:1 ratio of phenotypes is always observed in a dihybrid cross if the two genes are not linked. Now, in Mendel's mind, these were the only two outcomes. Either you would get the dependent assortment, meaning that the color depends on the shape, or the shape depends on the color, or you would get an independent assortment, meaning that the decision for color in no way influences at all the decision for shape. In reality, there's a third option, and we will discuss that third option in a future lecture on linkage. There is a partial linkage, an incomplete linkage that occurs. So there's actually a third option here that Mendel did not foresee, and we will discuss that in a future lecture at some length. The point being is that because Mendel observed this 9:3 to 3:1 dihybrid result, it means that the decisions of the two genes are not linked. And this is what led him to formulate his law of independent assortment. So the law of independent assortment originally stated that each pair of alleles segregates independently of every other pair of alleles. That's the way that Mendel saw it. Now, in reality, this is not correct. As people began to replicate Mendel's work, they realized that it's not true that every genetic decision is independent of every other genetic decision. So now what we would say is that the law of independent assortment is true only for genes on different non-homologous chromosomes or those far apart on the same chromosome. So it is only the scenario if they're on separate chromosomes or sufficiently far apart on the same chromosome. Now, if you're listening to that and thinking, well, what does sufficiently far mean? Well, we will talk about that in a later lecture. What Mendel did not know, that we now know, is that genes that are near each other on the same chromosome tend to be inherited together as a package. So he was trying to figure out, are these genetic factors inherited independently or dependently? And the answer is that sometimes they're dependent, sometimes they're independent, and sometimes they exhibit a third option that we refer to as incomplete linkage. For our purposes, and for the purposes of your exam, we're going to assume a Mendelian scenario, and a Mendelian scenario assumes that both the law of segregation and the law of independent assortment are in effect. Now, what does this mean? It means that gametes that are located on different chromosomes, genes that are located on different chromosomes should treat their assortment as independent probabilistic events. So if we look at this example here, the gene for color is found on this chromosome. The gene for shape is found on a separate chromosome. And the reason that they independently assort is that in meiosis 1, whether or not you give chromosome A or chromosome B, chromosome alpha, chromosome beta, is random because of the way that they behave in meiosis 1 and meiosis 2. So there is no connection. It's not true, for example, that if I receive chromosome A, I must receive chromosome alpha. Or if I receive chromosome B, I must receive chromosome beta. Those decisions are not connected at the chromosomal level. Now, what does this mean? This means that it's relatively easy to calculate the probability of multiple genetic matches as long as they are independently assorting, as long as they are not linked. Take this example. Consider that we have two organisms, Let's say that this is the father and this is the mother, and I have their genotypes across 5 genes, A, B, C, D, and E, and I want to know what the probability is that they will produce an offspring that is homozygous recessive for all 5 genes. Now, if the genes do move independently, what this means is that the genetic decision about whether or not they will be recessive for A plays no bearing at all on the decision for what happens with B or C or D or E. So in reality, what I have, instead of a complex genetic problem, is 5 very simple Punnett squares. And then I can use the multiplication rule or the addition rule to calculate the probability. So if we think about all of these Punnett squares, right, and I'll just encourage you to sketch them out. I mean, I've already got the answers there, but now the more of these you do, the more instantaneously you'll just know. If I have, this is, a monohybrid cross, so what's the probability of it being 1/4? A homozygous recessive, it's 1/4. This is also a monohybrid cross, so it's 1/4. If we look at C, one individual is heterozygous, the other individual is homozygous recessive. So the probability that it's recessive is 1/2. This is the same scenario flipped around, so it's also 1/2. And this is a monohybrid cross again. So in reality, because each event has no bearing on the probability of the other events, you can just multiply these probabilities together, and you get a probability of 1 out of 256. So if they are independently assorting, you could do a problem with 10 or 20, and it's really just 10 or 20 small Punnett squares whose answers you will multiply together at the end. Now let us turn to questions of hypothesis testing and the use of statistical tests to determine when the law of segregation and the law of independent assortment are being followed. Now, up to this point, we have been working in an idealized system. Basically, what we've been saying is, what should Mendel's laws lead us to observe? If Mendel is right, what should we observe? Let's use an example from German cockroaches. Let's say that you look in the literature and you find that 50, 60 years ago there was a scientist that described the inheritance of the color of German cockroaches, and brown is dominant to yellow. And the researcher reports that this follows a Mendelian pattern, and you want to confirm it. So you get some cockroaches, you follow Mendel's experimental design, you get pure breeding brown, you get pure breeding yellow, you cross them together, and you get a heterozygous dominant roach, and you take a homozygous recessive roach, and you breed them. So if we think about this cross, I have a heterozygous and a homozygous So what I expect is a 1-to-1 ratio of brown to yellow. That's what Mendel says should happen, assuming that the law of segregation and the law of independent assortment are true. That's what the previous scientist has reported in the literature. So if I do this experiment, I should expect for every 1 brown roach, a yellow roach. So let's say that I do this experiment. I get some poor graduate student to go in there and breed these 2 cockroaches, and we end up with 40 baby cockroaches. And I say, go in there and count how many brown and how many yellow. And what we observe, right, we expect to see 20 and 20, but instead of that we see 22 and 18. Now that's not exactly 1-to-1. Slightly more brown, slightly less yellow. But as we're all aware, when it comes to probability, you are not always going to get exactly what the probability states. If you have a coin that is fairly weighted and you flip it twice, you might not get a heads and a tail. You might get two heads or two tails. We understand this is how probability works. And so the question is, how many times will the data deviate from what we expect, and we begin to question whether or not the system really is fair? So how many times do I have to bet with Dr. Norcross that the coin will come up heads? She says it will be heads. I say it will be tails. How many times do I have to lose to her because the coin keeps coming up heads and it never comes up tails before I begin to suspect there's something wrong with the coin? So to put this in more scientific language, is this deviation from the expected outcome due to some unknown variable, some sort of random force or unknown variable, or is it because there's something biologically mechanistic, there's something going on at a cellular genetic level that explains why we have more brown cockroaches? To answer this question, we have to do a statistical test, and the statistical test we're going to discuss in this course is the chi-square test. Now, the purpose of the chi-square test is to help us understand whether or not the differences in our observed values are compatible with our hypothesis, or if the difference is based on some other unknown source of variation. What does the chi-square do for us as a test? What it will tell us is the likelihood that the data we observe is compatible with our hypothetical model. But it's important to also recognize what the chi-square cannot tell us. It will not tell us whether or not we have performed our experiment correctly. It will not tell us whether or not our explanation for what we have observed is correct. And this is a critically important thing for you to understand in terms of being a medical scientist. Hypothesis testing does not tell us that our answer is correct. It gives us a measure of how confident we can be that what we observed is not due to some sort of random force or unknown variation. So if we think about this, we expected to have 20 brown and 20 yellow offspring, but we didn't see that. Instead, we saw 22 brown and 18. Now, it could be just random. It could be random forces. It could be some unknown force. It could be that the previous scientist is wrong. So perhaps the inheritance is not based on Mendelian principles, and that there's some other biochemical, cellular, genetic force at work. It could be that the yellow color is linked to another gene that increases larval death. The breeder had more than 40, but they just gave us 40. It could be that the colors between brown and yellow are more similar, and it's difficult to know which ones are really brown and which ones are really yellow. It could be that we're 50 years too early and there's something going on with cockroach genetics that we don't understand because it hasn't been elucidated yet. And it's some explanation in the future that we really have no hope of understanding because, like Mendel and the chromosome, we're just too early. The chi-square is not going to tell us which one of these explanations is correct. It's not able to do that. So whenever we conduct an experiment, we're doing something called hypothesis testing. And we're using, in this case, a statistical test to do that hypothesis testing. And it's important that you understand, because many people are confused about this, that in hypothesis testing, we are not proving our hypothesis true. We are never doing that. We are never proving our hypothesis true. We are not in the business as scientists of proving hypotheses true. That is not the goal. Hypothesis testing, however, can give us some confidence that the data set we have is compatible with the hypothesis we hold. And if you've taken statistics, you'll remember that whenever we're doing statistical testing of hypotheses, we have two hypotheses. The null hypothesis states that there's no difference between the groups. So null, stands for nothing. The null hypothesis basically says there's nothing going on. There's nothing to see. It's just sort of, for unknown reasons, a insignificant difference. So the fact that I got 22 and 18 doesn't mean anything. There's nothing to see here. The alternative hypothesis says that there's a real relationship here. There's a reason, there's some sort of underlying mechanism that is explaining the differences between these two groups. So the alternative hypothesis, something is going on, but the chi-square cannot tell you what that something is. So the chi-square lets you know when it is safe to reject the null hypothesis, to reject the idea that there's nothing to see, and conclude there is something to see. So how do we know when it's safe to reject the null hypothesis? And we make a determination based off a value called the p-value. Now, you might think the p-value is so widely used that it's very easy to define. Unfortunately, it's not. And I'm not going to show it to you right now. You can click this link and watch the video. This will take you to an interview at a statistical conference, a place where statisticians go to present mathematical research. And you will see them stumble and fumble over trying to find a way to define what in the world a p-value is. And so you don't need to watch it. It's just a humorous sort of thing. The point is, it's difficult to define what exactly a p-value is. I will give us this definition to work with. A p-value is the probability under a specified statistical model, in this case, let's say the chi-square, that a summary of the data, like the average number of yellow or brown cockroaches, would be equal to or more extreme than the observed value. That may not be clear, so let's look at an example. This is an example that was formulated by Stuart Buck, and I've taken it as my own, and I've credited him so that you'll know where it came from. But let's sort of tease through what this p-value is explaining to us. Let's suspect, let's assume that you suspect that a coin is weighted, so that when you flip it, it's more likely to land on heads. Now, your null hypothesis would be that, no, there's nothing to see here. There's nothing going on. There is no difference between heads and tails, and so the coin is not weighted. But your alternative hypothesis is that the coin is weighted. So what will you do to test this? You will flip it multiple times. So let's say you flip it 100 times. And out of those 100 times, 72 are heads and 28 are tails. Now, of course, it should be 50-50 in an ideal system. So the question is that extreme enough? Now, if it was 100 heads and 0 tails, that would be pretty clear, right, that there's something going on. If it was 50-50, that would be pretty clear. There's probably nothing going on. 72 and 28, it seems like there's something going on, but how will we know? That's where the chi-square test or any sort of statistical test can help us. So let's say we do the math and we calculate a p-value of 0.15 or 15%. What this means is that there's a 15% chance that you could still get 72 heads and 28 tails even if the coin was fair. So what that means is 85% of the time when the coin is fair, you will not observe a difference this extreme. But 15% of the time, you will observe a difference this extreme. Now note, this does not prove that the coin is fair or not fair. It gives you a probability to gauge how likely it is that the coin is fair or not fair. So what's the threshold? Different disciplines have different thresholds, but for biology, the most common threshold is 5%. Now, we have decided as a scientific community that if your p-value is less than 0.05 or 5%, that is sufficiently small that we will reject the null hypothesis. Unfortunately, that's not the only point of data necessary to evaluate an experiment. You still have to look at the way the experiment was conducted. You have to look at the way that the methods were arranged. You need to look at the way data was included or excluded. So it's not simple enough to just say, well, what was the p-value? You still have to examine the experiment holistically. But the p-value is an important tool in you understanding what is the value, what is the weight of this particular data. So let's look at an example. You have probably seen in the news and in various publications the idea that eating a high fiber diet is going to promote a leaner body mass. So we have this hypothesis that eating 20 grams of fiber a day will cause mice to lose weight. And so we designed an experiment. 20 mice we're going to give a high-fat diet. 20 mice we're going to give a high-fat diet plus 20 grams of fiber. And 20 mice are going to get a low-fat diet. So we have these 60 mice. We feed them. At the end of the experiment, the high-fat diet mice weigh 256 grams. The low-fat mice weigh 208 grams. And the high-fat plus fiber weigh 217. So if you sit down and you calculate the stats here, the difference between the high-fat mice and the high-fat fiber mice is 0.034, or 3.4%. So what does that mean? It means that there's a 3.4% chance that the 38.4 gram difference in weight would still occur even if fiber was not a factor in this difference. Since 3.4% is less than 5, we reject the null hypothesis, and we can conclude that some other factor, possibly the fiber, is what caused that 38 gram difference. It is important that you understand this does not prove that it was the fiber that made the difference. It says there's a real difference, but it does not prove that it is the fiber that is the difference, because this will not prove your hypothesis to be true. It will answer the question, is there a difference between my experimental groups? If the only variable between the mice is the fiber, of course it's logical to assume that it is. But the frustrating thing about science is it's very difficult to control for all of the things that might affect something as complicated as percent lean body mass and how much fat is being carried. There are a number of things that influence this. It's a multivariate issue, not to mention the fact that the science of weight loss and weight maintenance is not well understood. We definitely don't have this thing completely sewn up. It's not something we have a perfect understanding of. And so there could be hidden variables. There could be variables that haven't been discovered yet. It's possible we didn't even think of all of the ones that do exist, and we didn't design the experiment well. So just getting this significant value does not mean we've proved it was the fiber. We have just proved there's an actual difference. Okay, with all of that out of the way, let us now actually look at the process of using a chi-square. I'm sure you have done this before in previous courses. It's probably been a while for a few of you, so we will walk through the steps of how you use the chi-square goodness of fit to analyze genetic results. The first thing you need to do is determine what results you expect to see. So let's say we perform a monohybrid cross for cat color, and the literature tells us that black fur is dominant to gray. And if we do a monohybrid cross in a Mendelian scenario, we should expect a 3-to-1 ratio of black to gray. So we have 50 kittens, and we get a scenario that is 30 black and 20 gray. That's what we observed. We did the experiment, and we observed 30 black and 20 gray. So if 3-to-1, if 75% of the kittens should be black and 25% should be gray in a Mendelian scenario. What we expected to see was 37.5 that were black and 12.5 that were gray. Now, obviously, you can't have a half kitten. This is just a statistical, sort of weird anomaly scenario. But instead, what we saw was 30 and 20. So the question is 30 and 20 really different from 37 and 12 to where we begin to doubt whether or not it's actually Mendelian? There could be something else going on here about the genetics of cat coloration. So we need to use a chi-square to figure out how different is 37 and 12 compared to 30 and 20. Now to do this, use the chi-square formula. The chi-square formula is basically, I know it looks weird written like that, but you take the sum of the observed of A minus the expected of A squared divided by the expected of A, and you add that to the observed of B minus the expected of B squared divided by the expected of B. Now, we have an A and a B because our phenotypes are black and gray. But if you looked at 4 phenotypes, then there would, you would also add another one, and then you would add another one. It just depends on the number of phenotypes you have. But for our scenario, we're just going to have these 2. So, we observed 30 black kittens. We expected 37.5. We square that number. We divide by 37.5. So 30 minus 37.5 is negative 7.5. When you square that, you get 56.25. Divided by 37.5, you get 1.5. For the gray kittens, we observed 20, we expected 12. You go through that, and your result is 4.5. And then you add 1.5 and 4.5 together, and so our chi-square value at the end of it is 6. So this is our chi-square value. It's not a p-value, it's a chi-square value. So we're not finished yet. Now, to determine the p-value, we have to compare our chi-square value of 6 to a chart of theoretical chi-square values that the statisticians have helpfully created for us based on the random distribution, the normal distribution. The other thing we have to think about is the degrees of freedom. Now, when you're doing a chi-square goodness of fit, the way that you calculate degrees of freedom is the number of phenotypes minus 1. So in this case, our phenotypes are 2. So 2 minus 1 is 1. So our degrees of freedom is 1. So now I have my chi-square value. I have my degrees of freedom. I'm ready to look at the chart and figure out what's my p-value. Here is the critical values of the chi-square distribution. What you can see here is that going down, you have my degrees of freedom going across. You have your p-values. This is the magical cutoff for us as biologists. We want a p-value less than 0.5. So you find the degrees of freedom of 1. So this is the row that we're looking at. Our value is 6.0. So 6.0 would fall right here, which means my corresponding p-value is somewhere between these two values. I don't know exactly what it is, but I don't really need to know exactly what it is for these purposes because it's going to be less than 0.05. Therefore, we reject the null hypothesis and we conclude that there is a real difference between our values of 30 and 20 compared to what we saw 37.5 and 12.5. Now, we may have a hypothesis for why that is. We might say, well, the reason we had more gray kittens than we expected to is that there's some sort of underlying preference for gray in the formation of the pigment. We may have our own hypothesis. The chi-square will not tell us if that hypothesis is correct. All it will confirm for us is that there is a real difference between these groups. Now, once again, we will have an opportunity to work these in class so that we're prepared for them on our exam. If you have questions, feel free to reach out to me.